All right, hello. This presentation is periodic table 3, and it is the third presentation in a series about the periodic table. First of all, periodic means repeated in a pattern, as we know, and we also know that there is a lot of information that we can just take straight from the table simply by looking at the table. There's also a lot of information that you learn, especially when you begin to learn about the periodic table's trends or tendencies, or how things are grouped together, or how elements end up being together more in chunks or sections. And once you begin to learn how to read and discover that information, then the periodic table becomes a very, very powerful tool. In fact, it also becomes a very, very powerful predictive tool. You can predict how atoms are going to behave, what kind of bonds are going to be made, and things of that nature. It truly is an important item for a chemist. All right, so let's have a quick review, and I do mean quick because we have discussed some of these things already. Let's begin with the idea that while I'm going to pluck some information right off the table here in a minute, I'm probably honestly going to spend more time talking about trends, because those are the items that aren't necessarily as readily apparent, but once you learn them, it really adds to your knowledge about the table, okay? All right, first of all, the table that we have today, the modern periodic table that we have today, is in large part due to men like Dmitri Mendeleev, obviously, but at the same time, we understand that our table doesn't look like an original table. And we also understand a very important fact, that this table was in large part put together by increasing atomic mass. And when you look at this table, it appears that that is also the case. But as we know, the modern periodic table is put together by increasing proton number. So 1 proton, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., etc. Now, does average atomic mass tend to increase along with that? And the answer is yes. However, there are some exceptions. So the most correct way to look at the table, in my opinion, is that we are looking at the table as being put together by increasing proton number. Okay? Now, when we look at the table, we can pluck one of those boxes out of the table if we chose. And so if we took something like silicon, for instance, we would automatically know some very important facts about the silicon atom. This would be a snapshot of a silicon atom. So one atom of that element. And what would we know? Well, we would know, first of all, its atomic number. We would know that it has 14 protons, because as we know, your proton in the nucleus is what gives the atom its identity. So we would know that it has 14 protons. We would know that it has an average atomic mass of 28.09. Now, we would also know that this number, and most of the time that number is not an even number because of isotopes. An isotope being an atom of the same element that has a differing number of neutrons, therefore it has a different mass. If you take the average of those masses based on their percent abundance, then you get your mass number. All right, what else would we know? Well, we would know that we are making an assumption when we look at the table, and we are assuming that the atoms that we are looking at are electrically neutral. Therefore, their positives and their negatives would balance out, which is really saying that the number of protons would be equivalent to the number of electrons. So if I had 14 positives, I would have 14 negatives. So I would have 14 protons and 14 electrons. Now, I would also know that if I took this number, which is protons, and subtracted it from the atomic mass, which is protons and neutrons, then I could do that subtraction, and that would give me my number of neutrons. So in this particular case, I would have 14 neutrons. I'm not going to have 0.09 of a neutron. I'm going to deal in whole numbers. I would have 14 protons and 14 neutrons. Now, some of this other information you learn as we go along, and we'll talk about that at the appropriate time. But that would be an example of one box off of the periodic table. What else? Well, you also remember that we mentioned, and this was a color-coded picture, but you also remember that we mentioned that we had this section in red, this section in kind of neon green, and we had this section in blue. This section in red are known as metals. We have our metalloids that have some characteristics of both metals and nonmetals, because don't forget, what are we doing as we move across the table? We are transitioning from the metals to the nonmetals. Now, I added a note because we're constantly looking ahead as well as looking behind, as well as looking at where we're at. At some point in time this year, we're going to talk about ionic bonds. Today, we're going to have to mention ions again because we're going to look at a trend on the table that involves ions. So in ionic bonding, we tend to have metals bonding to nonmetals, and the situation that we have is we have metals tend to give electrons and nonmetals tend to take them. Well, what would that create? Well, it would create cations and anions. And that is something that we'll talk about more when we get to bonding, but worth mentioning now, especially when today we're also going to mention ions again. Okay? All right, so this particular table I like because of the color coding, but for some people it probably seems a little daunting because it's like, oh, I have to remember all those names. But the reality is once you get to using a lot of those names, there's not that many. You know, you're only looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different labelings. Well, I'm sure you have more than 10 friends that you know their name. So when we look at this, we see columns or groups, okay? We see the alkali metals, we see the alkaline earth metals, we see the transition metals, we see the basic metals, we see semi-metals, we see non-metals, we see what we call the halogens, and we see what we refer to as the noble gases. And we talk about the noble gases a lot because they are our definition of stability. And we'll talk about that as we go along as well. But there's really nothing wrong with beginning to learn some of these names of these groups, because when you are in a group, you really have the same number of valence electrons, but what that means or what that transcends into is that you have a lot of the same characteristics. So what are we talking about? We're talking about trends or tendencies. So being in a group, okay, is going to be a situation where you're going to have similar properties. All right? I also don't mind and would encourage you to begin to think about your energy levels and your orbitals, but begin to think about your orbitals in terms of chunks as well. So, you know, in here, you're going to get into your s orbitals. Here, you're going to get into your d orbitals. Here, you're going to be in your p orbitals. And when you can begin to see that, it just begins to help you understand, especially electron configuration. It just helps you understand that a lot better. Okay? All right, so let's talk about trends and tendencies. And there will be some we'll just go quickly through. But ionic size, we're going to spend a little bit of extra time on because you kind of have to wrap your mind around that one a little bit. Many of you will like this slide. Some of you won't. You'll feel like there's too much on it. Some of you will like it because you'll say, well, now that's just everything right there in one place. Understand how to read the slide. Obviously, these three arrows are together on increase. These two arrows are obviously decreasing. And these arrows, just because they're going down, you have to look at the labeling. Most of them are decreasing as you go down, but this particular arrow is increasing. Okay, now what are these arrows? Well, things like atomic radius, ionic radius, electronegativity, ionization energy. All right, there are different trends that are reflected on the table, and this is sort of a shortcut for remembering some of those. Okay, let's start with atomic radius, one that we have discussed probably more than we need to. The atomic radius, as we know, is the half of d between two atoms of the same type bonded together in a diatomic situation. So atomic radius is the standard for how we look at this. Well, as we go across, okay, our atomic radius is decreasing. As we go down, it is increasing. Now, once again, this makes perfect sense because when we go across, we are in the same principal energy level. When we go down, we are going into subsequent principal energy levels. So when we go down, we have the shielding effect and electron repulsion. So obviously it makes sense that we would get bigger. As we go across here, we're increasing our number of positives and negatives in the same principal energy level. So doesn't it make intuitive sense that we would increase their attractive force and the size would go down? Okay, that is a trend that is reflected on the table. What's another trend? Well, another trend is ionic size. Now remember, an ion is defined as an atom that has gained or lost an electron. But right now, what do we want to focus on? Well, we kind of want to help ourselves too. We want to help ourselves remember things. Well, the atomic radius trend is analogous or similar to the ionic radius trend, which is as you go across, you decrease, and as you go down, you increase. So there's something to be said for just being able to remember the trend. But there's also something to be said for being able to understand the trend, but also could there be any differences between the two? And there's just a slight item we need to look at here to make sure we understand, okay? But before we do, in the last lecture, I mentioned something called ionization energy. And in fact, I was referencing first ionization energy. First ionization energy is basically defined as the amount of energy that it takes to take an electron from an isolated gaseous atom in its ground state, okay? Now, you may struggle a little bit with that, and you may not. What you're going to focus on is this first energy. First ionization energy was the amount of energy it took to pluck away an electron. Well, as you go across the table, ionization energy increases. As you go down the table, okay, it decreases. Now, if you think about this, honestly, it makes perfect sense. And I don't know, I'm kind of off a little bit for a second here. Let me see. Let me find my slide on here. Yes. Okay, it makes perfect sense if you think about some things. Think about the fact that our 18th column, okay, they are our noble gases. Our noble gases have a full s&p orbital. Now that's what's reflected in nature. They don't do that because we told them to. That's what we find. We say that they have reached the octet. If you are an atom in a period, okay, so if you're an atom right in here, look at how close you are. You're very close to reaching this octet. You don't really want to give up electrons. So trying to take your electron would not be an easy task. But what if you're over here? Okay, what if you're lithium? Well, lithium is closer to number 2 than it is number 10. So might it be easier for lithium just to give up an electron and fall back to a noble gas electron configuration? I didn't say it became a noble gas. I think sometimes we got to be careful with how we talk. We're not becoming noble gases. We're becoming like noble gases from their electron configuration. But if I was here, I probably wouldn't want to give my electron up. But if I was here, I would probably give my electron up a little bit more easily. And if I was down here and these electrons were pretty shielded from the nucleus, then you know what? It probably wouldn't be as hard to pluck one of those off either. So we go back to the slide that we were looking at. So the ionization energy increases as we go across and it decreases as we go down. So that's another trend. Now, let's go back to ionic size for just a few minutes because I told you something in one of the lectures. The overall trend, so let's make sure we understand the overall trend. The overall trend is for ionic size to go down and then to go up, okay? But in one of the lectures, I told you that cations would always be smaller than the atoms from which they came, and anions would always be bigger than the ions from which they came, okay? So it's easy to understand the cations. I mean, I think it's intuitive for all of us. So if we take one of the, like lithium, which is over here, if we take lithium and we look at before and after, okay, we see that the ion is smaller than the original atom. Well, why is that? Well, because in lithium's case, we had 3 protons and 3 electrons. We've lost one of the electrons. That's why it has a plus charge. It gave the electron up. Well, as soon as it gave that electron up, heck, it lost that energy level. And now there's also a charge imbalance. You now have 3 pluses and only 2 negatives. So wouldn't you think that 3 pluses could exert a pretty good pull on 2 negatives, right? So obviously it gets smaller. And so you're like, I would think, you're like, yeah, that makes perfect sense. I can totally see that. I can totally see why that would be. And I can totally see that that would be an unbalanced pull. I would now have more positives than I do negatives. And we all know what happens in an unbalanced pull, okay? All right, I think where it is harder, a little harder for us to see this, is when we get over to this side of the table. Because remember, our cations are in here, right? But our anions are in here. Why? Because these guys are gaining electrons, right? Well, why are they gaining them? Because they're very close to the octet. So they have a strong pull for electrons. So I think it's, here it is. So here it is. So here's my original nitrogen. Nitrogen could gain up to 3 electrons. Okay, here's my original oxygen. It could gain up to 2. Here's my original fluorine. It could gain at least 1. Well, what would that make? That would make an anion. Remember, anion is our negatively charged ion. Well, that anion is always going to be bigger. This anion is always going to be bigger. This anion is always going to be bigger. Now, in the last lecture, I made it sound like, okay, so then this one is bigger than this one and bigger than this one, and so that's why it's still decreasing. Well, honestly, that is why the trend is still decreasing. This one is bigger than this one, and this one is bigger than this one. So even though they got bigger, they're still getting smaller as they go across. And I think it's important to remember that because that is the overall trend. However, that's not the full story. And you really do need to know the full story, all right? So here it is. It's simple. Nitrogen had a certain amount of protons, and it began to gain electrons. Well, as it gains electrons, once again, it makes a charge imbalance, right? Okay, but where's the imbalance this time? The imbalance is not, more protons than electrons. It's more electrons than protons, okay? Also, as you add electrons, you know what happens. You're adding more negatives. You're potentially adding more electron repulsion. So now, what's going on? Well, not only do you have an imbalance, okay, but you also have a charge imbalance. Not only that, you might have more electron to electron repulsion. So your atoms, your ionic radius gets bigger, okay? So obviously your ionic radius is bigger, but this one is still bigger than this one, which is bigger than this one. So your overall trend as you go across on ionic radius, your overall trend is you're still getting smaller, okay? But there's a little bit more to that story than we have talked about up to this point. So let's make sure that we try to wrap our mind around that, okay? All right, so here it is. I have an atom that gains an electron. Okay, it didn't lose one, it gained one. So this one has an overall minus charge, but it has more minuses than it does positives. So now we have a charge imbalance. Not only do we have a charge imbalance, we also have the potential for more electron to electron repulsion. So the size of this atom, this anion in real life would be a little bigger than this one. So the rule is cations always get smaller, anions always get bigger, but the trend is as you go across, they still get smaller, and as you go down, they still get bigger. Basically the same trend that you saw with atomic radius. Okay? Now what about electronegativity? Electronegativity is an atom's pull for electrons. Well, we've been talking about the noble gases. We've been talking about how close they are to having the octet or a full S&P. That's what they have. They have a full S&P. In nature, that is the definition of stability. These are some of the most stable atoms. Now, I don't know if you've ever seen the movie Want to Be Like Mike, and maybe I've mentioned this before, but this young man wants to be like Michael Jordan. He really wants to be like Michael Jordan. Michael Jordan's one of the best players in the country. These atoms will do what they need to do to reach electron configurations similar to a noble gas. Why? Because it's all about stability. Okay? It's all about being stable. So what's the point for us? Well, the point is some of the most electronegative elements on the table are up in here. They have a very strong pull for electrons because they are so close to that octet. If you're down in here, plus you're way over here, you're not very close. Therefore, your pull for electrons is not very great. So electronegativity increases as you go across a period and decreases as you go down a group. Anything else? I want you to start thinking about valence electrons, and I want you to start thinking about how easy it is to find valence electrons for S and P orbital atoms. All you gotta do is count. 1, 2, 3, 4, 5, 6, 7, 8. Valence electrons are the electrons in the highest occupied energy level of an element's atoms. Why do we care? Because they're the ones that are going to bond. Okay, they're the ones that are going to be involved in bonding. So everybody in this column has one valence electron. Everybody here has 2. Everybody here has 3, 4, 5, 6, 7, 8. Once you know that, that's an extremely simple piece of information because all you're doing is counting. That piece of information will become very important to you when you learn more about bonding. So that's pretty simple, something for us to begin thinking about. And then the last item that we're going to at least mention today that we will talk about much more substantially when we talk about bonding is what we call oxidation states. Oxidation states are going to be values that we are going to give, okay? So remember what we mentioned earlier, metals tend to give, nonmetals tend to take. Therefore, we give oxidation values to these elements. Some of them are positive, inferring that they give. Some of them are negative, inferring that they take. +1, +2, +3, plus or minus 4, -3, -2, -1, 0. Now think about where I got those values. Think about your valence electrons. Think about how we counted across. Think about how close each one of those is to the octet. If you're not very close, you're going to give. If you're close, you're going to take. When you take, you're going to take what you need to reach the octet. So if I have 5 valence electrons right here, I only need 3 to reach the octet. That's where the -3 comes from. If I'm here, I only need 2. It's where the -2 comes from. If I'm here, I only need 1. That's where the -1 comes from. Well, how come this is a +1 and a +2? Because they aren't going to take. They're going to give. What are they going to give? They're going to give what they have in their valence outer levels. All right. So those numbers become very important to bonding, and they are readily obtained from the table, and there's no reason why we can't start thinking about those numbers, especially so when we're going to learn about bonding. Thank you.